This is the next chapter in our series of solving problems related to the IIT-JAM entrance exam. So we have been looking at different topics and how to solve problems in those topics. First we saw simple harmonic motion, then in the previous playlist we saw geometric optics. Now we will look at wave optics. So in this we will discuss about interference effects, which are attributed to the wave nature of light. So the first question in this is based on Young's double slit experiment. So the question says, suppose in Young's double slit experiment, I will explain what these parameters mean. The question has a few parts, 3 parts. What is the path difference delta for the rays from the two slits arriving at point P. So this y equal to 2 centimeters is basically the point P. Express the path difference in terms of lambda. Does point P correspond to maximum, minimum, or intermediate intensity condition? So before starting to solve the question, let us first draw the diagram for the setup of Young's double slit experiment. So we have, in Young's double slit, we will have two slits . I want to draw it as equally spaced as possible, but yes, the drawing is not to scale. Maybe I need to redraw it. So we have two slits. Let us call them S1 and S2. These slits, the slit separation is what is given by small d. So this is slit separation. So we are given d is equal to 0.15 mm. So this is the slit separation. Then we have a screen where we want to see the interference pattern. So this is S1 and S2 are slits. This is the screen, and this screen is at a certain distance. This distance is capital D. So we are given that capital D is 120 centimeters, and then from the center of the two slits we'll draw a perpendicular line. So this is like the midpoint. So this is what we take as the origin, and then from here we will measure the distance along the screen up to some point P. So this OP distance is what is called Y, and then we will see some interference pattern on the screen, some interference pattern on the screen. So this is the diagram representing Young's double slit experiment. So now that we have the diagram and we know what these quantities mean, lambda is the wavelength of light which is used to illuminate the slits. So let us start solving the question. Part 1 says, what is the path difference? So the rays will reach point P from the two slits like so, and these two rays will have certain path difference. So path difference is basically S1P minus S2P, mod of that is the path difference. In order to find that, we can drop a perpendicular from S1 onto S2P, and then this perpendicular is going to be roughly the path difference, assuming that from this point, let us call this point some point M. So when the screen is far away from the slit plane, much far away from the slit plane, then we can consider under that approximation that S1P will be roughly same as M times P. So our path difference in that case is going to be equal to S2M. Now if we connect the center to the point P in consideration, then we will consider this angle as theta. So if this angle we consider as theta, this angle from joining this midpoint of the slits to the point P, taken with respect to this midpoint to this perpendicular line to the screen. So if this angle is theta, then approximately S2 S1M, that angle is also theta. We can see that from a quick construction over here. Let me draw the quick construction under the assumption that we are considering. So our assumption is that screen is far away at an infinite distance away from the slits, so to say, practically infinite distance. So we have the slits. We draw the slits once again. We have the slit. So when the screen is kept far away, say at an infinite distance away, then these lines from these rays from the slit and from the center of this, the midpoint of the slits, will be essentially parallel rays. So these lines are essentially parallel. The rays from the slits and the line from the center, all these are going to be parallel when the screen is at, let's say, very far away, or practically speaking at an infinite distance away from the slit plane. Now, by geometrical construction, this angle is what we are taking as theta. Since this angle is theta, and by geometry we were drawing this as a perpendicular bisector, bisector meaning it's right in the middle of these two slits and it is perpendicular. So this angle right here is 90 degrees and this is theta. So this angle over here will be 90 degrees minus theta. Now since these two lines are parallel, we will have this angle over here. This angle will be 180 degrees minus of 90 degrees minus theta, because sum of angles when drawing a transversal, sum of interior angles to a transversal of parallel lines is 180 degrees. So this gives us 90 degrees plus theta. Now if we draw from this S1 point a perpendicular, let me do it in a different color so that we do not get confused. Now if we drop a perpendicular, this is perpendicular, so because all these lines are parallel, so this angle is also 90 degrees, and since the total angle is 90 degrees plus theta, we get this angle right here. If I label these points, then angle S2 S1M is equal to theta. This angle over here, this shaded region, is going to be theta. So we have this angle over here is also theta. This is from simple construction, given the fact that screen is at almost infinite distance away from the slits. So all these rays coming from the slits are parallel, and even the line from the center of the slits is also parallel. So because of that, we have this approximation. Typically the screen will not be at infinity, it will be at a practically what we can call infinite distance. So approximately this angle is going to be theta. So then we can write down path difference. This is roughly S2M, and S2M will be nothing but d sine theta. This distance S1 S2 is d, and angle S2 S1M is theta, so S2M is d sine theta. Now when the screen is at a much greater distance as compared to the slit separation, then we can use the small angle approximation. So small angle approximation. This is valid when the screen is much far away and the distance OP is very small in comparison to the separation between the slit plane and the screen. So from small angle approximation, we have sin theta is roughly equal to theta is roughly equal to tan theta, and tan theta we know is nothing but y over d. So we get path difference. Path difference is called delta. So we get delta is approximately d sin theta, which is approximately d tan theta, which is equal to then dy over capital D. Now we are given the values of small d, capital D and y, so we can just plug in the values. This is going to be, small d is given as 0.15 mm, y is 2 centimeter, and d is 120 centimeter. So plugging these values in the calculator, we will get path. Sorry, this is mm. So this is equal to 2.5 micrometer. We have solved the first part, which was finding the path difference. The next part asks us to express this path difference in terms of the wavelength. So we need to find delta in terms of lambda. So we need to find out this factor. So this is basically ratio of delta and lambda. So we can find delta over lambda. This is 2.5 micrometer divided by wavelength is given 833 nanometer. So plugging this in the calculator will give us approximately equal to 3. So this gives us delta is approximately 3 times lambda. Finally, we are supposed to determine, sorry, this is a different color. We are supposed to determine whether this point P is a point of maximum, minimum or intermediate intensity point. So we see that delta is approximately equal to 3 lambda. So this is integer multiple. Integer multiple of wavelength, that is path difference is integer multiple of wavelength. So this corresponds to a point of maximum intensity. Note that this ratio is not exactly 3, it is almost roughly approximately equal to 3. So it is not exactly perfectly maximum intensity if you talk in theoretical terms, but from a practical point of view, this is maximum intensity. So we say that the point P is a point of maximum intensity. So this solves the question. This question was based on the Young's double slit setup. So this is a simple setup, and in this we have two slits separated by a certain distance. Then we have a screen kept at a certain distance from the slit plane, and then we want to observe the interference pattern on the screen. So this is the interference pattern that we see on the screen.